Okay, so we got some constant magnetic field. Let's say it's pointing out. I build this system of rails in here. Maybe I put a resistor over on this side. And I put this bar that's a conducting bar that I'm free to move. So this bar can move. I can grab onto it and I can squish it, move it. Let's say, for example, that I'm moving it at some constant speed v in that direction. That's going to induce a current because remember, flux is BA cosine of the angle between them. B is pointing straight out. DA, the normal vector, is pointing straight out. Those are in the same direction. Angle is 0, cosine is 1. B is constant. A is what's changing here. So I'm going to have a changing flux. That changing flux, if this has length L, my changing area will be my velocity times my length. You can work out the details on that if you don't believe it. It's kind of interesting, but that's how fast my area is changing, my speed times this length right here. So my changing flux will be BVL. And that's a negative because my area is decreasing. That induces a current. So we're going to get a current flowing through here. So here's a good way to light a light bulb. This is what those things do. That you squeeze your little handle and it lights up your light bulb. But light bulb's just a resistor. Let's figure out the direction our current would flow. So I'm losing some of my, I'm crossing over some of my ups, so my new induced current is going to make up for some of those that I lose. It's going to point up. So my current will flow around counterclockwise like this, even through this bar. This is a conducting bar. Let's figure out what that new current is going to feel a force. Moving charges feel magnetic forces. So I've got this current flowing around. This magnetic field is going to induce a force on that. It's going to try to push these bars apart or pull them together. It's going to try to push on this bar. So remember, in direction on a current, the magnetic force goes like I cross B. That's the direction of the force. So I is facing that way. B is facing up, so I have to rotate my hand around. The magnetic force on this bar is going to point back this way. So I'm pushing on the bar is pushing back on me. That's how I can keep it at constant speed. That's where I'm doing work here. That's where I'm generating the energy to force these little charges to move around. I'm applying a force. Force times distance is work. So I'm pushing, the bar is pushing back on me equal and opposite amount. I'm going at some constant speed. That's generating this current. What if we flip this around? Think of this scenario differently. What if I take my hand off the bar and I suddenly increase this magnetic field? Make it really, really big. That's going to induce a current. It would flow in this direction. That's going to create a force that I'm not there to balance out. This bar is suddenly going to start moving on its own. So if I were to say, I don't know, build a system that looks like this, put this bar here, put a projectile over here, suddenly increase the magnetic field really, really strongly and really quickly, this bar is going to move and it's going to shoot that projectile out. It's called a rail gun. These can be incredibly powerful. You can shoot this projectile, huge, massive projectiles at incredible speeds just by using a magnetic field, a changing magnetic field.